when we looked at the partial derivatives with respect to x and respect to y, these guys present the rates of change specifically of z, and that's kind of important to remember, it's of z, in the directions of x and y. At any point on the surface, that's obviously defined by this point. These rates of change are very specifically in the I and j directions, which is fine, but quite often we're more interested in some arbitrary direction. So if I have some point x naught, y naught that defines a value of z, which is a value on the surface, then I may be more interested in some arbitrary vector u, which obviously is going to have its own direction and magnitude. Now, or actually here, we'll come back to this, but I'm going to represent u here as a unit vector. Let's jump into Maple real quick. And here's some surface. And I want you to think about what's going on here just for a moment. With this surface, what we've been doing is saying, okay, I'm going to spin this down so we're looking down at the xy plane a little bit more. Now, if I take a plane, say I'm going to cut this where x equals 2 or something like that, you can see that when I cut a plane through here, I'm going to have this curve that dips down and comes up very sharply. So when we talk about the partial with respect to x, we're talking about what's happening in the direction of z along this curve. Likewise, if I spin it this way, you get a little bit better look. If I take like y equals 3 and cut a plane this way, then my partial derivative is talking about the tangent to this curve that's created at the intersection of the plane and this surface. But if I have some arbitrary angle, some arbitrary vector u, that's maybe cuts across like this, or at some other angle, well, still, if I set up a plane that cuts across the surface, I'm still going to have a curve along this surface. And that's exactly what we're talking about now. We're talking really about what happens along that curve on that particular surface. So conceptually, we're thinking of this just the same way as we did with the rates of change in the x and y direction. It's the exact same idea, except for now we're just simply going to look at another possible direction. So suppose here for a moment that I have another point Q that's on the curve. I already have the point P. And I believe I designate that up here. Yeah, let's just say P is x naught, y naught. And I have this other point Q that's on the surface. So what I'm interested in is perhaps this vector that's created by PQ, where I'm going from P to Q. So if I think of this as 2 points on the surface and the vector in between them, I can think of these values in terms of their projections onto the xy plane. So I'm going to let, say, P prime and Q prime be projections of P and Q onto the xy plane. Now, because of that, I know that the vector P prime Q prime is going to be parallel to the vector PQ. Now, these primes are just denoting, another version of the P. These primes aren't derivatives. Don't be thinking that these are derivatives in any way. So, that means that I can actually represent this as PQ prime is going to be equal to H times U, where if I let U equal AB, that's going to be the vector HA, HB, for H is obviously for some scalar. And I'm thinking here in terms of U as being, or having representation, PQ. So because these are parallel, I can write these as a constant multiple of each other. Now, with that in mind, with H being some scalar, I can now start thinking in terms of, well, x minus x naught must be equal to HA, where x is my coordinate for q, x, y, and then the coordinate for p is x naught, y naught. So if I subtract those two, that's how I get the directional vector back when we were doing that sort of thing much earlier. So x minus x naught will be equal to HA, which obviously means that x is equal to x naught plus HA. Y minus y naught is going to be HB. That obviously gives me that y is equal to y naught plus HB. So in terms of what's happening in the z direction, I can think in terms of delta z, the change of altitude over h equals z minus z naught over h, which equals f of x naught plus HA, y naught plus HB, minus f of x naught, y naught over h. So this is just simply another way of writing delta z over h. So the rate of change, because this is nothing more than a rate of change, the rate of change in the direction of u, so this is the rate, I'm going to write that down, rate of change in the direction of this vector u, which is in the direction of PQ, those 2 points on the surface, relative to z, because we're talking about the rate of change of z, is I can then write as the partial u of f of x naught, y naught, which equals the limit as h goes to 0 of f of x naught plus HA, y naught plus HB minus f of x naught, y naught over h. And notation-wise, so you understand what just happened here, we've looked at this notation briefly before. This capital D is sometimes used for derivative, like d sub x is derivative with respect to x. It's very rare to use that notation. As a matter of fact, this usage of it here is about the only time I can think of off the top of my head to actually see this notation here. So this is the derivative with respect to the vector u, which again is this PQ, of this function. So this is a directional derivative. This is the directional derivative. Better write that down. This is the directional derivative. That's what this notation right here actually means. So of course, this is if the limit exists. Now notice here that if let's go this up a little bit. If I let u equal I, this is vector u equal I, which then is obviously the vector 1, 0. If I put 1, 0 in here, then what I actually get is du is actually equal to di. And because of that, if I put in 1 for A and 0 for B, then what I actually end up with is this is no more than what we think of as the partial with respect to x. Because again, this is a 1, so I have x plus h, and then b is 0, so I have y naught. And likewise, if I let u equal j, this gives me 0, 1, which implies that du is actually equal to dj, which is the same as the partial with respect to y. So let's take a look at, wrap this up with a quick theorem here. If f is a differentiable function of x and y, then f has a directional vector in the direction of any unit vector u, which equals AB. Again, I'm specifying u as being some type of unit vector here. And we can find that by duf of xy. So this is notation. It's a directional derivative of f in the direction of u is equal to the partial of x, of xy, I should put that in there, times a plus the partial with respect to y of xy times b. Remember, these are components right here. There's my b and there's my a.